Hi, welcome back to CMSC 828T, Vision Planning and Control in Aerial Robotics. Today we will be talking about one of the most important aspects of autonomous flight, which is trajectory planning. Till now, we have talked about the controls, the dynamics, and the inner and outer loop and those kind of things. And we've also talked a little bit about planning for paths using D star, A star, Dijkstra, and so on. Today we'll be talking about how do we take these paths which are generated through path planning algorithms and convert them to actually dynamically feasible trajectories. So let's dive right into it. So the first question one would ask is, how do we get smooth 3D trajectories? Consider a quadrotor as shown here in blue, and let the intermediate states be yellow and the final state be orange, which is you want to go from the blue state to the orange states through the intermediate states which are shown in yellow. How do we actually compute these yellow states such that they are dynamically feasible? So this is also called trajectory generation in robotics, or it's also called as interpolation in computer graphics. So this is a very common topic studied extensively in literature, and we are going to be talking about some of the algorithms which we'll be using for quadrotor trajectory generation today. So of course the first question anybody would ask is, why do we need this? Let's say we have a quadrotor as shown here with the frames of reference and so on, and we want to travel in this black line trajectory as we discussed before. And let's say we have a desired trajectory wherein you specify the position, velocity, and acceleration. This is very similar to the project 1 phase 2 which we designed, wherein one would automatically give the desired trajectory, position, velocity, and acceleration. In this phase, we will be generating these values given obtained from a path obtained wherein the path is obtained from a Dijkstra or an A star algorithm. So of course, the path generated by Dijkstra, A star, RRT, PRM need to be time parameterized, which is what is called trajectory planning, and they need to be made smooth and dynamically feasible. So let's say we have a quadrotor as shown here in blue, and you want to go to the orange state, but you want to follow a trajectory which is shown here, which is in black. It's a non-smooth trajectory. If I ask you the question, can I follow this trajectory? Answer would be yes, but the caveat here would be that you will have to stop. Let's say I impose an additional constraint. I say you cannot stop at this corner. How would you traverse this trajectory? It's dynamically not possible because you always have a moment of inertia when the quadrotor pitches to the right and moves. You always will overshoot or undershoot and you will cut the corner. So the idea is, how do we take this path and convert it into a dynamically feasible trajectory? So a dynamically feasible trajectory could be the one shown in red, blue, or green. So of course now the question comes in, which one of these would you like more? Green would be the fastest, blue would be an optimal value in terms of speed and the following trajectory following. Red would be more optimal in terms of the small amount of deviation from the trajectory. So depending upon the application, we would choose either the red one or the blue one or the green one, or the black one if we cannot afford to overshoot, but we would say, okay, let it take a lot more time, but we can stop and use it. That's the idea here. So we'll use calculus of variations to obtain smooth trajectories. So here is a video made by ETH Zurich, wherein they have two quadrotors and one of them is going to toss a pole to the other one, and these are both going to plan trajectories such that they can balance the pole on each other. So let's look at the video. So you see that it's a very hard maneuver to do, and we'll be covering simple concepts which are underlying the framework here. Of course, what they have done is way more complicated than what we are doing here, but the general fundamentals still remain the same. So let's move on. The problem setup is as follows. We have a blue quadrotor wherein the start state is defined. It could be something like position, velocity, acceleration, and so on. It depends upon what all we want to specify. Next, we want to traverse this trajectory wherein the states in between and the final states, the waypoints are given and the goal state is given, wherein we again define position, velocity, acceleration, and so on. And we want to follow this as good as possible. So First question one would ask is how smooth is the trajectory? Of course, the answer would be as a change of the input function would be one of the heuristics we can use. So the smaller the change in the input function, the smoother the trajectory is. So that's sort of like analogous to the amount of work done. So of course, if we have a nth order system which determines our system input, we have boundary conditions on all n minus 1th order and lower derivatives. So that's the general idea here. If you don't understand why that is so, just hold on for a minute and I will be talking about that in the next few slides. So let's talk about calculus of variations. So let's say we have a start state which is shown in blue as the previous quadrotor was, that is x of 0. So we start at time t is equal to 0, and we want to be at a state, the orange dot as shown here, x of capital T, wherein we want to reach there at capital T time, and this is a time parameterized quantity given by x of t, as let's assume that small x of t shown here is the optimal value. So which is x star of t. In this case, x of t will be x star of t if it's the optimal value. It's defined as argmin of integral 0 to t, some function which is denoting the work or the smoothness of the parameter of the function as we discussed before, and it's a function of the first derivative, the position, and the time in this case. So assume that x of t is an optimal function again. So here x of t will be the x star of t if it's optimal. Any other path going from x0 to x of t can be written as the same optimal x of t plus alpha into eta of t, where eta of t is again a polynomial if x of t is a polynomial and alpha is some scaling function. The idea here is any other trajectory would basically take in more work than the optimal trajectory. So and that is shown, one of the cases are shown here, the other one is shown here, and you can observe that it's need not be in terms of distance, but in terms of work done, this will be more than what the x of t is. So let's move on. So again, this is the same equation from the previous slide. Since we know that x of t or x star of t is the optimal function, we have the criteria such that d by d alpha at alpha is equal to 0 of this whole thing would be basically 0. Pause this video if you don't understand this function. Take a moment to soak in why this is so. All this is saying is we just took the derivative of it and equated it to 0 like any optimal function would be. This is sort of like the necessary condition for something to be an optimal function. So now we use Euler-Lagrange equation. So the necessary condition satisfied by the optimal function is given as follows. Just d by dt of dou L by dou x dot minus dou L by dou x is equal to 0. So if you don't remember or recall Euler-Lagrange equation, pause the video, go look at Wikipedia or any other textbook and study about Euler-Lagrange and come back. Now let's take a simple example. So this plot might be a little bit confusing. It's not a 2D plot. It's a one-dimensional position plot, but the plot here is time on the x-axis versus the value of the position on the x-axis as shown here. So at time t is equal to 0, we want to be at x naught, and time capital T we want to be at xt. So the control input would be x dot is equal to u, and this is the same equation as before. The only difference being the Lagrangian is being chosen as x dot squared. This is basically representing sort of how smooth or how we define the smoothness of the trajectory to be. So again, as we defined before, x of 0 is equal to x0, x of t is x sub t. Cool. So let's move on. Let's apply the Euler-Lagrange equation, and we would basically get the condition as 2x double dot is equal to 0 or x double dot is 0. So if we integrate it and solve it, we would basically get the time parameterized quantity as the equation of a straight line denoted by c naught plus c1t. This is analogous to y is equal to mx plus c, as we have seen in our primary and middle school. This is the same thing, and this is the shortest path is a straight line as expected before, because the work done here was chosen to be velocity squared. Cool. Let's move on. So what if you have, or what if we have a nth order derivative as the control input? We would basically choose the Lagrangian as xn square, where xn denotes the nth derivative of x, and we would basically have the position constraints, the velocity constraints, and so on, and the nth derivative constraints. So we have all the constraints as shown in the previous slide, but this is for the nth order derivative. Again, we would apply the Euler-Lagrange equation for the nth order derivative, and that is written here. If you don't recall any of these equations, please pause the video, and go look at Wikipedia for more explanation. Okay, so the smooth trajectories for n is equal to become 1 becomes the shortest distance or the minimum velocity, n is equal to 2 becomes minimum acceleration, n is equal to 3 becomes minimum jerk. What does it become for n is equal to 4, 5, and 6? Think about it for a second. For n is equal to 4, it would be minimum snap, because the fourth derivative of position is snap. And for n is equal to 5, it's called crackle, so which is the fifth derivative of position, and the sixth derivative of position is pop. So if you don't know, it's a funny thing, snap, crackle, pop, but just remember this for the time being. So now we can choose the Lagrangian as x nth derivative square, which leads to the final equation being a 2n minus 1 order polynomial, which is 2n degrees of freedom. So if you don't understand how this works, please use the Euler-Lagrange equation as we showed in the last slide, and please try to derive it yourself. It's a super simple derivation, takes like 2 minutes to do. Cool, let's move on. Now, how do we extend this to multiple variables? Let's say we are doing this in 2D, we have x star and y star, and the Lagrangian is a dual function of both x and y and so on. So the easiest way, or what Euler-Lagrange does for us, is basically it separates out each dimension separately. So we have one set of Euler-Lagrange for x, one set of Euler-Lagrange for y. Sorry, and here it's color coded as x is being red and y is being blue. So it makes it easy for us to understand. And of course, back to the slide we started with, we wanted to do waypoint navigation and we wanted to parameterize all these. That's how we started doing that. Let's move on with the 1D example right now. So design a trajectory x of t such that x of 0 is some a and x of t being some b. So again, if we want to find the minimum acceleration trajectory, that means I'm defining my Lagrangian as x double dot square. It's in one dimension, so it's x double dot square. So apply the Euler-Lagrange equation and we get the fourth derivative of x is equal to 0 as the condition, and we would basically obtain x of t as a cubic polynomial, which is a third order polynomial equation. The one thing here is that we want to find these ci's, which is c0, c1, c2, and c3 in this case. So how do we solve for ci? So we defined the problem in such a way that we had some position constraints, that is, we start at this point and go up to this point where this is a and this is b, and we also defined velocity constraints so that it starts with the 0 velocity and ends with the 0 velocity. We want to start from rest and end at rest. Need not be the case, but this is a point A to point B navigation system wherein you want to start from rest and end at rest. So we want to solve the following equations according to the trajectory equation given below. We just put this as a simple matrix formula, and this is of the form y is equal to ax, wherein ax is equal to b, wherein you want to solve for x as a inverse into b. In MATLAB, you can just call the backslash operator and it would gloriously solve it for you. If we are doing this for bigger matrices, note that this can be super ill-conditioned, and just doing a simple inverse might not be sufficient, and you might have to do a decomposition and play around with it. Okay, let's move on. So if you look at Peter Cork's Robotics Vision and Control textbook, you would see the motion profiles as follows. So this is basically plotting the position, where S here is the position versus time for a quintic trajectory. Note that this is not for a cubic trajectory, but for a quintic trajectory. And S dot is shown as a smooth velocity, starts from 0, increases, then drops down. You might be wondering, why does it slow down? The idea here is because we want to start at rest and end at rest. When you accelerate, you will have some velocity and then you want to bring the velocity down to 0. The only way we bring down the velocity is by decelerating or going the velocity down to 0. That's what is shown here. If you look at the acceleration plots, it's super clear. So we start accelerating, reach a maximum value, then start decelerating, reach a maximum value in the opposite direction, and then slow down, come back to 0. That's the idea. So start at rest, end at rest. This is for a quintic trajectory. Now let's look at another trajectory generation or profiling algorithm called bank-coast-bank trajectories. The reason why this is important is because you might have a limit of how much velocity you would want to impose or how much acceleration you can impose, and this makes it super easy to impose that for one. And the second condition is this is much more easier to compute than a cubic trajectory. So the idea here is that you have the same motion profile as before. It's more like a straight line, and we start off this the velocity profile being shown here, and you linearly increase, then maintain a constant velocity, which might be your maximum velocity, and then slow down. That's what is shown here. Note that these are piecewise, and so the acceleration has these jumps, and of course the width of how much you want to keep this constant can be controlled easily. That is defined by the parameters of the function. So let's move on. Now we want to talk about multi-segment 1D trajectories, wherein we have 4 points shown by blue, yellow, green, and orange here, and at time t0, t1, t2, and t3. And we want to be at positions x0, x1, x2, and x3. Note that again this plot is time versus position because it's all 1D. So let's say we have m trajectories like this as shown before, and we want to design a trajectory such that we have at times t, we want to be at these positions x0 to xm. So define a piecewise trajectory xt such that these are piecewise constants as shown. And if we use Bank trajectory, the velocity profiles are going to be something which looks like this. So take a moment to understand or think why this is not the best possible solution. So the idea here is that it's too slow, and if you have a large number of points, it stops at every single waypoint. So it's not the most efficient way to get there in terms of time. Of course, it's efficient in terms of error because you don't have any position error and you don't deviate. Assuming that there is no overshoot in your controller, it will work really good in terms of position error, but it's super slow. You generally don't want to ever use this kind of formulation unless you cannot afford to have an overshoot. Okay, so the other alternative formulation would be basically using a cubic spline when we have the same set of parameters inside, but we want to instead define a piecewise trajectory wherein between every two consecutive set of waypoints we have a cubic spline associated with it. So of course it has 4 m degrees of freedom, and it's shown here. Of course it's a second order system, and you would have these constraints as shown. So in the starting and the end position, you have position and velocity constraints, the velocities being 0, and in between two segments you have constraints such that the cubic spline from blue to yellow and yellow to green would basically have the same position constraint, and the velocity is consistent and the acceleration is consistent. And the same thing between yellow and green segment and green and orange segment as shown here. Pause the video for a second and try to understand why this is so. This is just to maintain the fact that when we are moving continuously in space, we want to have a consistency across the points. That's what this is representing. Of course, it has totally 4m constraints, wherein we get 2m constraints from position. We have 2 into m minus 1 constraints from derivatives and 2 constraints for the endpoints. Of course, you can extend this for an nth order system. The last slide was basically for cubic spline, so the velocity was maintained constant. So in this case, for an nth order spline, you can have any arbitrary nth order where you have n minus 1 derivatives being 0 and start and end, and you have 2 into n minus 1 derivatives being continuous in between, and the positions of course being continuous. So you have 2n into m constraints, where n is the number of waypoints and n is basically the order of the system we are looking at. Cool. So how do we deal with multi-segment, multi-dimensional trajectories? Of course, we can use Bank trajectories, wherein we project the desired acceleration or velocity profiles along straight lines connecting two waypoints. How do we deal with polynomial trajectories? We solve for each dimension independently, as Euler-Lagrange allows us to do. And of course, we'll be using Euler-Lagrange equations to decouple and make life easier for us. And one major point we should not forget here is that make sure that the time constraints are same. That is, if you want to move, let's say 1 meter in x direction, 2 meters in y direction, the velocity has to be more in the y direction than 1. I cannot say it is exactly double because it's a nonlinear function, but you have to maintain the fact that if you want to cover 1 meter in x in 1 second, and the same 1 second you should be able to cover 2 meters in y direction. So you'll have to calculate the velocities accordingly. One thing which might be a problem here is that the velocities are coupled, but generally if you're working at slow speeds, it's not that much of a problem. So you might be asking the question, how the hell does it all go on a quadrotor? How do we actually use this on a quadrotor? If we refer back to the quadrotor control slide we had before in the last lecture, so the idea here is you had a trajectory planner here, and this trajectory planner is what we discussed in this lecture, and this would basically be generating the position, velocity, and so on for us. So given n number of waypoints, we would basically time parameterize it as a function of time and give values for RT of t shown here. So of course we can also please refer to Minimum Snap Trajectory Generation by Daniel Mellinger and Vijay Kumar. This is an amazing paper which talks about taking into extra additional constraints to get aggressive trajectory generation. It takes into account the size of the room wherein you have boundary conditions that you cannot go beyond this spot and so on, and you also take in additional constraints such as the maximum velocity, maximum thrust, and so on. It's a very nice paper to go read. So note that it's fairly complicated in terms of math, so please take your time and read it and ask questions if you don't understand. Of course, go fly some autonomous quadrotors, and I would point you to refer to this textbook by Peter Cork, Robotics, Vision and Controls, and of course Daniel Mellinger's amazing paper. So as we discussed before, please read the trajectory generation again, try to understand how it all fits in with the regime, and this is what you'll be doing in Project 1 Phase 3. Thank you. See you next time. Bye bye.